Hello and welcome to lecture 38 of analog integrated circuit design. We have been looking at op amps at the transistor level in some detail. We saw how we can make a single stage op amp and improve the DC gain by adding a second stage and a third stage and so on. Now, we had already discussed all these things at the control source level. Now, we also know how to make it at the transistor level. We also saw that the different stages of the op amps will be biased properly only when DC negative feedback is applied around the op amp. This is something that we knew already, that an op amp must always be used in DC negative feedback. Now, you can see why. If you do not do that, one or more of the stages inside the op amp will not be biased correctly. Okay. Now, in this lecture we will mainly talk about one particular aspect of the op amp and also many other circuits, that is the common mode rejection. Now, before we go there, I will briefly touch upon how to get even higher gains, let us say with a two stage op amp. It is a very simple technique. It is a combination of things that we have seen already. We will look at that and then look at common mode rejection of different circuits and why it is important and so on. Okay. Now, our two stage op amp look like this. This is the first stage and that is the second stage. Okay. And this is the output. Now, if you want to have an op amp with a higher gain, then we can of course go for a three stage op amp, but that needs a more complicated frequency compensation scheme and so on. We need to make sure that each of the smaller loops is stable. Okay. Now, a simple technique to increase the gain of this op amp is to simply replace the first stage. Instead of using the simple differential pair single stage op amp, we can use a cascaded single stage op amp. Okay. For example, I can use a telescopic cascade op amp. I will not show all the biasing details here. Let us assume that these voltages are appropriately set to keep all transistors in saturation. Okay. Now, what happens is the gain of the first stage is higher. Okay. Originally, we had a total gain of plus GL, which is the conductance of any load that you connect. Now, this part of it will be replaced by okay. So, it will be replaced by the expression for the gain of the cascade amplifier. This number is going to be much higher than that one. So, the overall gain also is going to be correspondingly higher. Okay. So, this is a simple way of increasing the gain DC gain of the two stage op amp, and the integrating capacitor or the compensating capacitor is exactly the same as before. Okay. So, similarly we can use a triple cascade or a folded cascade as the first stage. Now, whether you choose to do this or not depends on the available headroom, the input common mode range that you require and so on. Okay. Actually, it is becoming very common to do this because as you go to deep submicron processes, the value of GM by GDS of a single transistor with a short channel length is rather small. So, you need to have higher gains, and a very convenient way of getting reasonably high gain is to use a cascaded first stage followed by a common source second stage. Okay. Now, we will move on to a very important topic with op amps and many other circuits in fact, which is the common mode rejection. Okay. Now, we have dealt with this earlier. I showed the example of an inverting amplifier and a non-inverting amplifier. Now, the amplifier was assumed to react not only to the difference between the input voltages, but the op amp also reacts to the average value of the input voltage or the common mode input voltage. In this case, we saw that there is a distinct difference in the behavior of the non-inverting amplifier and the inverting amplifier, and that is because the non-inverting amplifier has a very large input common mode voltage for the op amp, whereas the inverting topology has a very small common mode voltage swing. Okay. Now, let us look at the common mode rejection of the op amp that we have designed, and also we will look at another circuit for which we will calculate the common mode rejection and see what the bad effect of having a poor common mode rejection is. We have already looked at the common mode gain of a stage like this, okay, loaded by RL, and we know that if we apply small signal common mode voltages to the two sides, the outputs will rise up together and the common mode gain will be okay. This is approximately the common mode gain. I have ignored the GMs of M1 and M2. I assume that the output resistance of M0 is so large that the common mode gain can be approximated by RL by 2 times RDS 0. Okay. So, you can improve the common mode rejection by improving the RDS of the tail current source M0, okay, and that is basically mainly what decides the common mode gain and consequently the common mode rejection ratio. Now, the single stage op amp we have it is a slightly different topology. We do not have resistors, but we have a current mirror load. Let us say again we apply only a common mode small signal input, that is identical inputs to the two sides of the differential pair. Now, how do we figure out what the output voltage is? First of all, we know that when the circuit is perfectly symmetrical, that is M1 and M2 are identical, M3 and M4 are identical, the voltages here and there will be exactly identical. Okay. We have argued earlier by contradiction that if this voltage was different from the other, you will find some inconsistency, okay, because you can consider the currents in M1 and M2 and the effect of VDS upon them, and similarly the currents in M3 and M4 and the effect of their VDS upon them, and you will find that the only consistent solution is to have V0 equal to that voltage. Okay. Now, when you apply equal voltages to the two inputs VCM and VCM, the same thing still applies. Okay. In fact, we can think of this as simply changing V bias, we have not changed anything at all. So, that is one thing. Now, also the currents will divide equally between M1 and M2. If the current here is a certain value of I naught, the current here will be I naught by 2 and the current there will be I naught by 2. Okay. Let us say the current source M naught is ideal, that is this I naught does not depend on the voltage across M naught. In that case, even if you apply a signal here, this voltage will change, the voltage at the tail node will change, but the currents do not change. So, the voltages at the drains of M3 and M4 will remain as they are. Okay. So, as before, if RDS 0 is infinity, the output voltage will be 0, okay. That is the common mode gain will be 0, but of course, in reality this current source will be imperfect and we will have some change in the voltage. What happens is when you apply VCM, this voltage will change, and how do we evaluate the changes and so on? The easiest way to work this out is to make use of the fact that the drain voltages of M1 and M2 are identical. If these two voltages are identical, what you can do is to simply tie them together and analyze the circuit. This is a very common technique of analyzing circuits. So, I am going to do that and the circuit will become a lot simpler. So, if I do that, what happens is M1 and M2 are in parallel and M3 and M4 are in parallel. And I will rewrite the circuit with M12, which means that it is a combination of M1 and M2, and we have M0 as it is, and here we have M3 and M4 in parallel, and their drain is connected to the gate, because you see that all these three are connected together. Okay. And V bias plus VCM is applied there. Now, as we saw before, the transistor M12 behaves like a source follower. So, any signal at the gate appears at the source with a gain of almost unity. Okay. Now, we know that this answer is different when you have body effect and also when you have a finite resistance RDS 0 for M0. I will let you work that out, work out the exact result. Here I will approximate the voltage at the source by VCM. Okay. Now, if this is VCM and the transistor M0 has an incremental resistance RDS 0, the incremental current here in this transistor will simply be VCM divided by RDS 0. Okay. And that incremental current flows into the GM of M3 and M4 in parallel. Okay. So, the output voltage will be nothing but minus VCM by RDS 0, and the impedance looking into the diode connected transistor will be the combined GM of M3 and M4, which will be 1 over 2 GM3. Okay. So, V naught by VCM is simply equal to minus 1 over 2 GM3 RDS 0. Okay. So, a couple of things to note, just like before, the quality of the current source decides the common mode rejection, but also the situation is better than before. By using the active current mirror load, what we have got is an enhanced common mode rejection. Okay. Now, let us say we have a differential pair with a resistive load and output taken from one side. The differential gain will be GM1 RL divided by 2 and the common mode gain will be RL by 2 RDS 0. Okay. It will be negative, and if you have a current mirror load, the differential gain will be GM1 by GDS1 plus GDS3, and the common mode gain will be minus 1 over 2 RDS0 GM3. Okay. And the contrast is obvious if I calculate the CMRR, which is the ratio of differential gain to the common mode gain, and I will just show the absolute value of that, which is GM1 times RDS0 in this case. Okay. You see that RL by 2 appears in the differential gain and also in the common mode gain, whereas with the current mirror load, in the differential gain we get 1 over GDS1 plus GDS3, and in the common mode gain we get 1 over GM3. The common mode load impedance is much smaller than the differential load impedance. So, that gives a further enhancement of CMRR. Okay. So, this will be two times GM1 GM3 RDS0 by GDS1 plus GDS3. Okay. So, this common mode rejection of the differential pair with a current mirror load is much higher than that of a differential pair with a resistive load. Now, this is a good thing. So, this means that it does not respond as much to the common mode. Okay. Now, when you add a second stage, that second stage does not differentiate between common mode and differential inputs, because the first stage has already converted the differential input to a single ended output. Okay. So, at the output of the first stage, once you have a signal, it cannot be distinguished whether it comes from a differential input signal or a common mode input signal. Okay. So, the second stage will react in the same way to the common mode input to the op amp and a differential input to the op amp. So, that means that the common mode rejection ratio will not change. Okay. So, the common mode rejection is determined only by the first stage. This is a common characteristic of all op amps, and with an active current mirror load, the common mode rejection ratio is much better. Okay. Now, while synthesizing the op amp topology, we came up with the current mirror as a convenient way of providing a bias for the current I0 by 2. Okay. So, it is actually a lot more than that. It is not merely providing a bias, it is also providing an enhanced common mode rejection. Okay. Now, what is the effect of common mode rejection on the operation of the op amp? We have already seen what happens with inverting and non-inverting amplifiers. Now, we will look at another example about operating with different supplies and common mode voltages for the amplifiers and see what happens. Okay. I earlier said that any op amp can be operated with a single supply or a dual supply. Okay. Now, let me take a very simple amplifier which is a voltage follower. Okay. Now, what does it mean to say that I can have a single supply or dual supplies? First of all, what it means is I can have any value of V bias here and V bias there, and I can apply an input signal, and the output here will be the same V bias plus Vi. Okay. Now, this is true if the common mode rejection of the op amp is infinite. Okay. So, regardless of any value of V bias, the output will be equal to V bias, and any increment that you apply will come out exactly as you applied it. Okay. Now, in case of CMOS op amps, we talk about a single supply operation, which is some VDD and 0, and we apply a bias V bias. The load is connected to the same V bias. Okay. Now, what does it mean to say that the op amp has a finite common mode rejection? What it means is that the output voltage will change depending on the common mode value. Okay. So, what it really means is, just for simplicity, let me remove the load resistance. Because of finite common mode rejection, as I change the value of V bias, okay, the output will change. Now, how does it change? Ideally, if I apply any value of V bias there, V bias should come out, because this is a unity gain follower, and let us assume that the op amp does not have any offsets and so on. In reality, what happens is different. Okay. Now, let us assume that there is some value of V bias 0, for which the output is exactly equal to V bias 0. Okay. So, let us assume that there is some voltage for which the output of this is exactly equal to that one. Okay. This is the ideal operation of the voltage follower. Now, let me change the value of V bias. Okay. You can think of this as changing the value of V bias or changing the input. I have put the load back just to emphasize that the other side of the load is connected to V bias 0. Okay. In this case, again no current flows through RL, and the situation is exactly as before. If for V bias 0, the output will be V bias 0, and the op amp does not supply any current. Now, let me change the value of V bias 0, that I will think of as applying some common mode voltage. Okay. So, I will apply a common mode voltage to this and a common mode voltage to that one. Okay. Now, what should happen is that the output should be at the exact same incremental voltage as before. Okay. The common mode rejection ratio is extremely important in many circuits. Okay. Now, in the cases that we have taken so far, it depends on the topology of the op amp. Now, what happens if you have a finite common mode rejection ratio is that if you change the input common mode voltage of the operation, the op amp behaves differently. Okay. So, the output offset, for instance, depends on the common mode input of the op amp. Now, earlier we said that the op amp can be operated either with a single supply or a dual supply, and the behavior will be exactly the same. Okay. So, let us say we have any circuit. For simplicity, I will take a voltage follower. I said that you can operate with a 0 common mode voltage and only an input, that is 0 bias voltage and only an input, or let me call this VDD and 0. Okay. And have a bias voltage for both the input and output, and if I apply an increment here, I will get the same exact same output in the two circuits, provided that the supply voltages are the same, that is V plus minus V minus, that total supply voltage equals VDD minus 0. Okay. Now, reality is somewhat complicated, because so far we have not discussed the influence of V bias at all. We only said that this value of V bias has to be within the input common mode range of the op amp. We know that there is some input common mode range for the op amp, okay, and that is decided by the input stage. Now, and V bias can be anywhere within that range. So, in reality what happens is, if the value of V bias changes, because of the non-zero common mode gain of the op amp, the output will change in some way. Okay. So, let us say I do not have the input. Now, as I go on changing the V bias, the output will change in some way. Okay. Now, when I do not have an input, that is like saying I have V I which is equal to 0. Okay. When I have V I equal to 0, what should the output be? It should be V bias, but there will be some offset voltage from V bias. Now, what does it mean to say that I have a non-zero common mode gain? When I change V bias, the output will change. So, that means that I have a changing output offset voltage. Okay. So, if you think of a DC voltage follower, what happens because of the non-zero common mode gain of the op amp is that the output offset will change. Now, when you have a dynamic signal like a sine wave, now in every part of the sine wave you will have a different offset, and this is like having a distortion. Okay. Now, this is a very important thing. So, it is not true that the input can be biased anywhere within the common mode range. Now, depending on the common mode rejection ratio, as you change the input bias voltage, the output will change. Now, to minimize this effect, the common mode rejection ratio has to be as high as possible. Okay. Now, in general, this common mode rejection is something that bothers you whenever you intend to take the difference of two signals, but you also end up responding to the average of the signal. Okay. Now, a voltage is always measured between 2 points, and you always want to take the voltage between 2 specific points. Okay. Now, there are many cases in which the voltage across those 2 points is rather small, but the average of these 2 voltages with respect to ground is very large. Okay. Now, why is the average voltage relevant? Because in general we will not have any circuit that responds only to this voltage. Okay. Now, all circuits will have some common reference point, which is the local ground of the circuit, and what you really respond to is individual voltages V1 and V2 with respect to ground. Okay. Now, you design circuit so that it responds predominantly to V1 minus V2, okay, and it does not respond to V1 plus V2 by 2. As we have discussed earlier, we can think of the voltages V1 and V2 individually or as the difference and common mode voltages. Okay. Now, because it always responds to the two individual voltages V1 and V2, we cannot always guarantee that the output response will be of the form V1 minus V2 times something. Okay. So, usually what will happen is it will be V1 minus V2 times the differential gain plus V1 plus V2 by 2 times some common mode gain. Notice that this is exactly the same as writing some alpha 1 V1 plus alpha 2 V2, but since we usually want the differential response to be large and the common mode response to be small, it makes sense to write it in this form. Okay. So, the real problem is when ACM is non-zero and this V1 plus V2 by 2 happens to be large. Okay. Now, what I will do is I will discuss an example circuit for which this common mode rejection is very important, and this also serves as a kind of an example for calculations of mismatch. Okay. Now, this is not related to the common mode rejection of the op amp itself, but the common mode rejection of some circuit which is supposed to respond to the difference voltage, that is the difference between two input voltages, and it is known as a there are many cases in which you have two inputs Vp and Vm and you want to extract Vp minus Vm. Okay. Now, how do we do that? Let us say I had Vm alone and I wanted to get minus Vm. What could I do? I could use an inverting amplifier of gain minus 1. So, let us say I make this R and R I know that the output will be minus Vm, and this is the op amp. Okay. Ideally, it keeps these two voltages the same, and the output will be exactly equal to minus Vm. Okay. Now, what I want is not just this one, but Vp minus Vm, that is Vp must appear with some positive gain. Okay. Now, we have also earlier discussed the relationship between inverting and non-inverting amplifiers and how they are really the same circuit, but with inputs applied to different places. Okay. So, let me take the same circuit and use the non-inverting version instead. Okay. The circuit is the same, except that I have applied the input here. Now, what do I get? I know that the gain is 1 plus this resistance divided by that resistance. Okay. Remember, for gain k we used to have R and k minus 1 R over here, and k minus 1 R equals R. So, k equals 2. So, here I get 2 times Vp, but what I wanted was Vp. Now, if you want a smaller voltage, that is quite easy. So, what I have to do is not apply Vp here, but apply Vp by 2. Okay. So, how do I get Vp by 2 from Vp? Easiest thing in the world, I just use a resistive divider. Okay. And I combine the operation of these two circuits. I combine these two circuits. Okay. Now, from Vm to the output it is an inverting amplifier, from Vp to here it is a resistive divider, and from there to there it is a non-inverting amplifier of gain 2. Okay. So, here I get Vp by 2. So, at the output I will get Vp minus Vm. Okay. Now, this is a circuit that is used very often to convert the difference voltage into a single ended voltage. So, if you have two large voltages Vp and Vm and you want to take the difference between them, you can use this circuit. Okay. And you can see that the output will be exactly equal to Vp minus Vm. So, what is the catch here? Now, let us assume that the op amp is ideal. Okay. So, we are not now talking about the common mode of the op amp. We know that if the op amp has a finite common mode rejection ratio or a non-zero common mode gain, the output will respond to the input common mode. Okay. The input common mode here is nothing but Vp by 2, and the output will respond to that in addition to giving Vp minus Vm. So, that is one problem. So, I will let you work out the details of that. Please take it as an exercise. Consider an op amp with a common mode gain ACM and a differential gain AD, and calculate the output. Okay. So, you will find that the common mode gain will have some effect on the output of the op amp, and by reducing ACM or reducing, in particular reducing ACM by AD, you will improve the behavior. Okay. So, I will not look at that, I will look at something else that can also give you a finite common mode rejection ratio or a non-zero common mode gain. Now, what is that? You see, the resistive divider as well as the non-inverting amplifier both depend on the resistor ratios. Okay. The attenuation of the resistive divider as well as the gain of the non-inverting amplifier. Now, in reality we have 4 different resistors, 4 physically different resistors. So, their values will be different. Okay. So, this will be R1, R2, and this will be R3 and R4. Okay. Of course, nominally all of them equal R, but in reality there will be some difference. Okay. R2 is R plus delta R2 and so on. So, now what will be the output of this circuit? Again, please take it as an exercise and calculate it for yourself. I am going to write down the answer here. What we get here at this point will be Vp times R2 by R1 plus R2, and from there to the output we have a gain of 1 plus R4 by R3. So, that is the gain from Vp, and the gain from Vm of course is minus R4 divided by R3. Now, if R4 by R3 happens to be 1 and R1 by R2 happens to be 1, this will be exactly equal to Vp minus Vm, but in reality we know they will be different from each other. Okay. So, let me consider let us say one of these ratios R4 by R3. This will be R plus some value, okay, and it will be R plus some other value. Okay. Now, delta R4 and delta R3 are differences from the nominal value R. Okay. Now, I can write this as all I have done is to take R out and expanded out the ratios, and I will also use the fact that delta R4 by R and delta R3 by R are quantities much smaller than 1. So, what I will get will be 1 plus delta R4 minus delta R3 by R. Okay. And this delta R4 minus delta R3 is nothing but the mismatch between these two resistors, and divided by R you get the normalized mismatch between the two resistors. Okay. And as is obvious, this expression depends only on the relative mismatch between pairs of resistors. Okay. So, V out, which is 1 plus R4 by R3 divided by 1 plus R1 by R2 times Vp minus R4 by R3 times Vm. Okay. Now, R4 by R3 I said was one plus delta R4 minus delta R3 divided by R. Similarly, R1 by R2 will be 1 plus delta R1 minus delta R2 divided by R. Okay. So, here we will have 1 plus delta R4 minus delta R3 divided by R divided by 1 plus delta R1 minus delta R2 divided by R, okay, minus 1 plus delta R4 minus delta R3 divided by R. Okay. This times Vp minus this whole thing times Vm. Now, I do not want to keep on writing delta R4 minus delta R3. So, I will rewrite this as delta R3 4 divided by R, that is the normalized mismatch between R3 and R4. Similarly, this is delta R12 divided by R. Okay. So, if I substitute that, that is what I am going to get. Now, I am going to once again use the fact that this delta R34 by R and delta R12 by R are quantities much smaller than 1. So, this entire thing reduces to okay. So, that is what it is going to be. So, the output is of the form of some alpha p V p minus alpha m V m. Okay. and alpha p is not exactly the same as alpha m. Now, this can be written as alpha p V p plus V m by 2 minus V p minus V m, sorry, plus V p minus V m divided by 2 minus alpha m V p plus V m by 2 minus V p minus V m divided by 2. Okay. I have just resolved the signals into their differential and common mode components. So, which gives me alpha p minus alpha m times the common mode voltage V p plus V m by 2 plus alpha p plus alpha m times V p minus V m by 2. Okay. So, the common mode gain of this circuit is alpha p minus alpha m, which is equal to 1 plus delta R 34 by R minus delta R 12 by R minus alpha m, which is 1 plus delta R 34 divided by R. Okay. And it turns out to be simply minus delta R 12 divided by R. Okay. And the differential gain which is alpha p plus alpha m divided by 2. This is the number that multiplies V p minus V m, and that is equal to 1 plus delta R 34 by R minus 1 by 2 delta R 12 divided by R. Okay. Now, it is quite close to 1, it is different because of the resistor mismatch, but right now we are interested in the effect of the common mode. So, we will ignore the inaccuracy in the differential gain and say that this is approximately equal to 1. So, the common mode rejection ratio is nothing but 1 divided by that one. So, we will simply work with the common mode gain. Okay. So, the circuit has a non-zero common mode gain. Ideally, it should have given an output V p minus V m. In reality, it gives some constant times the common mode voltage plus 1 times V p minus V m. Okay. Now, what is the effect of this? This common mode gain is quite small. Okay. It is the relative mismatch between resistors 1 and 2, it is delta R 12 divided by R. Okay. So, what happens because of this? Now, what happens in reality is that, let us say we consider a case where you are trying to distinguish a small difference between two large voltages. Okay. So, let us say the inputs are 1 volt and 1.001 volts. Okay. So, the output will be V p minus V m times 1, this part is minus 1 millivolt plus some resistor mismatch times V p plus V m by 2. Okay. Now, V p plus V m by 2 is approximately 1 volts. Okay. It is 1.0005 volt. So, in fact, let me write that here. Now, how much is delta R 12 by R? It depends on the physical size of the resistors that you use. Okay. Now, let us say that we have 1% mismatch, which sounds small, but let us see what happens. So, let us say delta R 12 by R is 0.01. Okay. Just I will take some particular number. Now, what happens? Here we will have approximately minus 10 millivolts. Okay. So, the contribution of the difference is 1 millivolt, the contribution of the common mode is 10 millivolts. It is much more than the difference, and it is going to drown out any difference voltage that you are trying to measure. Okay. Now, it also turns out that this kind of circuit is used in many precision applications when let us say in thermocouple amplifiers and so on, when you have a small voltage difference and you are trying to detect only that difference. Now, because of resistor mismatches, the effect of common mode is lot more than the effect of the difference voltage, and everything is completely washed out. Okay. So, the only solution is to choose resistors that have a very small mismatch between them. Okay. Now, there are some other advanced techniques that deal with this kind of circuits which need very good matching, but right now we will assume that we have to use this circuit as it is. So, the only way is to make the resistor so large that the mismatch becomes very small. Okay. Now, also one more thing, now when we measure mismatches, we specify either the standard deviation or the variance. Okay. Here I just calculated the output and it comes out to be some delta R12 by R, which is the amount of mismatch for a particular instance of this amplifier. What we should rather specify is the standard deviation of the common mode gain, and that is nothing but the standard deviation of delta R12 by R, and that is nothing but sigma R itself, okay, which is the standard deviation of relative mismatch. Okay. Now, what does this mean? And let us say we make sigma R to be something better than what we had earlier. So, let us say 0.1%. Okay. Now, what this means is that the common mode gain will also have a standard deviation of 0.1%, and if you plot the distribution of common mode gain over let us say a number of amplifiers, let us say you make a million amplifiers and plot the distribution. The distribution will be Gaussian because the distribution of sigma R is Gaussian, and .9% of the amplifier will have a common mode voltage whose magnitude is less than 3 sigma R, okay, or in other words 0.3%. Okay. Now, whether this is good enough or not depends on the application. So, let us say we are interested in measuring a minimum difference voltage of 1 millivolt. Okay. Now, let us also assume that our sigma ACM is 0.1%. So, that means that for 99.9% of the amplifiers, the common mode gain magnitude will be less than 0.3%. Okay. Now, there is nothing sacred about this 99.9%. We will just assume that if there is only 0.1% of the amplifiers that fall beyond this, we will throw them away and use only the ones that are within this range. Okay. Now, for this amplifier to be usable, the effect of the common mode, that is VCM times ACM, has to be much smaller than the smallest difference, which is 1 millivolt. Okay. Now, ACM I will take it to be 0.3%, which is the 3 sigma value. As you know, the Gaussian distribution has an infinitely large amplitude, but we will use 3 sigma as the amplitude. So, VCM times ACM, which is 0.3%, which is 0.003, has to be much less than 1 millivolt. So, I will simply say it is 1/10 of this value. So, that is 0.1 millivolt. Okay. So, let us say less than or equal to 0.1 millivolt. So, VCM has to be less than or equal to 0.1 millivolts by 0.003. Okay. And how much is that? That will give you approximately 33 millivolts. Okay. So, while this amplifier ideally gives you only the difference and completely rejects the common mode, with the mismatch that we have, it can only tolerate a common mode voltage of about 33 millivolts. Okay. Now, let us say we have to tolerate a common mode input voltage of 3.3 volts. Okay. That is, we would like to tolerate common mode voltages of 3.3 volts. This means that the sigma ACM has to be correspondingly smaller. So, this 3.3 volts is 100 times larger than 33 millivolts. So, the sigma ACM has to be 0.001% or similar, because the sigma of the common mode gain is the same as the resistor mismatch, that has to be 0.001%. So, if you have to be able to tolerate a very large common mode voltage, you have to use very precisely matched resistors. Okay. Now, this is just an example circuit where the common mode rejection is important. I showed this just to put the reason for common mode rejection in context, and this is a very common application, that you have two voltages and you have to take the difference, but the two voltages are with respect to some ground, and the circuits always respond to the individual voltages, or in other words the difference voltage as well as the average voltage. Okay. Now, in general also it turns out that the response to the common mode can be strongly influenced by the matching. Okay. Circuits which ideally give you 0 common mode gain can give you a non-zero common mode gain in presence of mismatches. Okay. So, this we will see further in the following lectures. Thank you.